Okay, this is our chapter 14 video in physics, and we're going to be talking about heat. So first we need to define heat. What is it? So it is sometimes thought of as like a physical substance or material that flows, almost like water or air flowing, but that's really a misconception. If you remember when we talked about waves, waves transmit energy, but the physical medium in which the wave is in doesn't move. So if you make a splash in a still pond with a rock, the waves will radiate out from where it splashes. The water itself is not moving in that direction, just the wave or the energy. And that's the same thing with heat. Heat is basically a transfer of energy. Heat is a form of energy, and that energy can flow from one molecule to the next, from one material to the next, but the materials themselves remain in place. We're going to introduce here a new unit of heat called the calorie, which you've probably heard of before because calories are used to describe the amount of energy found in our food. But we'll talk about that here in just a little bit, how the calories you see on your food packaging is actually a kilocalorie. 1 calorie is defined as the amount of heat energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. Okay, and like I said, the calories that you see on your food label is a kilocalorie or 1,000 calories. Now the difference is subtle, so you got to watch out for it. Is the capitalization of the C in calories. If we are talking about a lowercase c, that is just 1 small calorie, the amount of energy required to raise 1 gram of water by 1 degree Celsius. If you see capital C calories, that means we're talking kilocalories, which is equal to 1,000 small calories. So 1 lowercase calorie equals 1,000 big C calories. So another thing to know about heat is that it flows in the direction of hot to cold. So heat energy, if two materials are in contact with each other in such a way that the heat is allowed to flow, it will go from the hot side to the cold side until they reach a thermal equilibrium. So if you're standing in front of your refrigerator with the door open, trying to figure out what to eat, your parents may tell you to shut the door because you're letting all the cold air out. That's not technically accurate. Actually, what you're doing is you're allowing heat from the ambient room to flow into the refrigerator. And so that's just something to keep in mind, the direction of the flow. Heat will always flow from hot to cold, not the other way around. So James Prescott Joule, for whom the unit of energy, the joule, is named after, was also a brewer. He made beer. And he is the scientist who came up with this idea of thermal energy, of the calorie. And this, to me, is a really ingenious way of quantifying or figuring out what a calorie would be. And so this perhaps he was inspired by some of his brewing apparatus that he used to make his beer. But what he had is he had this tank of water here, and he recorded its temperature. It was at a certain temperature, and he set up this rig where he basically had a weight suspended by a rope that went around a pulley and was attached to this axle running through the container here, and it had these paddles on them. So what would happen is, as the weight would fall, it would have a certain weight in newtons, and it would fall a certain distance in meters. And a newton meter is a joule. And so then what would happen is, as this weight falls down, it spins these paddles inside the container here, and that spinning, that agitation of the liquid inside by these paddles would give the liquid energy. It would raise its temperature. And so he was able to equate the amount of energy in newton meters or joules required to raise the temperature of the liquid. And what he was able to then find is that one small c calorie is equal to 4.186 joules, and 1 kilocalorie, therefore, is 4.186 kilojoules. So that's how we were able to determine the energy required to raise the temperature of a gram of water by 1 degree Celsius. Let's look at an example problem here. We've got ourselves a mountain climber that is going to climb up a mountain and do some work equivalent to 500 calories. Notice here we've got the capital C calories. So what we're talking about is 500 kilocalories. Okay, and so a kilo is 1,000. So what we're saying is this is 500,000 calories, little c calories. Okay, and we're assuming the mass of this climber is 60 kilograms. So what is it how high do we have to go? How high do we have to lift this mass in order to create this much energy, or to burn off that much energy, or to do an amount of work equivalent to that? I suppose are all different ways of expressing this problem. So first of all, let's convert our calories into joules so that we can work with newtons and meters, units that we're used to. So we've got 500,000 kilocalories. No, not kilocalories, just little c calories. We already converted that. Multiplied by 1 calorie is equal to what? It's equal to 4.186 joules. Okay, so we convert that and we get, let's see, so I got 2,093,000, which if I round that off to, well, again, the author gave us a round number here, so is that 1 or 2 significant figures? I'm going to assume that that is significant, that we've got 2 significant figures to work with. So that is equal to 2.1 times 10 to the 6th joules. All right, so if that's the energy that we're shooting for, we need to basically take our mass and raise it up a certain distance. We've got newtons and meters, so however many newtons we lift times the number of meters will give us this many joules. So our hiker, who I guess is us, since it's we are the hiker, the weight is 60 kilograms times 9.8 meters per second. And so that should give us 588 newtons. And so the height is what we're trying to figure out. What is the height? So essentially what we're saying is joules equals Newton meters. So 2.1 times 10 to the 6th joules equals 588 newtons times how many meters? And so the meters will equal 2.1 times 10 to the 6th divided by 588 newtons. And so that's equal to 3,571 meters, or again, if we're going to take this just two significant figures, that's going to be approximately 3,600 meters is how far up we've got to go in order to do work that is equivalent to 500 kilocalories. Now, that's not necessarily to say that you have to climb up a 3,600 meter mountain in order to burn off the 500 calories in your Mountain Dew that you just drank. It's a little bit more complicated than that when it comes to the actual biology of burning calories. But from a strictly physics point of view, these are equivalent units of energy or work. So 3,600 meters times 588 newtons will give us 500 kilocalories. So let's talk a little bit more about exactly what heat is. Heat is energy transferred from one object to another. So when you feel something and it feels hot, what is happening is that hot object is transferring its heat energy to you. And a way that we can measure the amount of energy in an object, the amount of heat energy in an object, is by its temperature. So temperature is a measure of kinetic energy. And so heat is basically a form of kinetic energy. It comes from the molecules being excited, having a lot of energy moving around. And also remember that the heat is going to flow from the hot object to the cold one. So this may seem like a subtle difference, but if we look at internal energy, the sum of all the energy is the total energy. The total internal energy is adding up all the energy of all the molecules. So it's different than temperature in that we have three boiling pots of water. Let's say they're all 100 degrees Celsius. That's 100 degrees Celsius, that's 100 degrees Celsius, this is 100 degrees Celsius. So they all have the same temperature. It doesn't matter if I've got one pot of boiling water or I have three. They all have the same temperature. But if I look at the internal energy, it does matter how much I have, because if I have 3 pots of boiling water, I have 3 times as many molecules. So I have 3 times the amount of energy. So the difference here is the total amount of internal energy is affected by how much stuff you have, whereas the temperature does not. They all have equal temperature. But if I have 3 pots of boiling water, I've got 3 times the amount of energy. And heat, let's remember, is the transfer of energy due to the difference in temperature. So if this if the energy here were to transfer out of the system, that would be heat.